Hi guys, this is AS Chemistry, Organic Chemistry, and we are looking at alcohols. Question 8. Compounds containing the allyl group have pungent smells and are found in onions and garlic. Allyl alcohol, CH2 double bonded to CH, single bonded to a CH2OH group, is a colorless liquid which is soluble in water. Allyl alcohol behaves as a primary alcohol and as an alkene. Give the structural formula of the organic compound formed when allyl alcohol is reacted separately with each of the following reagents. And we have reaction with acidified potassium dichromate and heating under reflux. So if we are using acidified potassium dichromate, it is a mild oxidizing agent which would oxidize the primary alcohol into an aldehyde, and the aldehyde that is formed will further be oxidized into a carboxylic acid. So the product formed would be CH2 double bonded to a CH group, which is single bonded to a COOH group, because CH2OH being a primary alcohol group ends up being completely oxidized to a carboxylic acid. Allyl alcohol undergoes the following reactions. When reacted with concentrated HCl at 100 degrees Celsius, CH2 double bonded to CH, single bonded to CH2Cl is formed. So the OH group is replaced by a Cl atom. State as fully as you can what type of a reaction this is. So this is an example of a nucleophilic substitution reaction. When reacted with MnO2 at room temperature, CH2 double bond CH single bonded to CHO is formed. So here we have a primary alcohol being converted into an aldehyde, which is oxidation. So what type of a reaction this is? This is an oxidation reaction. Allyl alcohol can be converted into propanol in two steps. So in step one, we have the double bond being removed and single bonds being formed, and then we have oxidation of the primary alcohol into an aldehyde. So what reagents and conditions would be used for each step? So reagents used for step one would be hydrogen gas, as hydrogenation is being carried out, and the conditions would be use of a nickel or a platinum catalyst along with the temperature range of 150 to 200 degrees Celsius in order to carry out hydration of the allyl hydrogenation, not hydration, hydrogenation of the allyl alcohol. And in step two, we have conversion of a primary alcohol into an aldehyde and not a carboxylic acid. So we cannot use a harsh oxidizing agent. We will need to use a milder oxidizing agent. So the reagents would be acidified K2Cr2O7, and another thing that would be needed would be we heat it along with distillation. We let the vapors evaporate at the boiling point of the aldehyde, condense them and collect them to obtain the aldehyde and prevent it from being oxidized into the carboxylic acid. And since the aldehyde would have a lower boiling point than the carboxylic acid, so we can actually collect the aldehyde by collecting the vapors in a separate container after passing it through a distillation plant. So in this way, we will have the aldehyde collected in most of the quantities that it was produced. Only some of it might be oxidized further into a carboxylic acid. So allyl alcohol and propanol are isomers. Allyl alcohol has a double bond and an OH group present, and propanol has a CHO group present. So both of them may have the same molecular formula, but they have different functional groups. So what form of isomerism do they display? They are showing functional group isomerism. And this is a part of structural isomerism. Alyl alcohol may also be converted into propanol by using ruthenium 4 catalyst in water. So suggest what is unusual about this single step. So here we have conversion of the double bond into a single bond, which is hydrogenation, or we can call it reduction. And we have conversion of the primary alcohol group into an aldehyde group, which can be called oxidation. So what is unique about this reaction is that both oxidation and reduction are taking place in a single step. So both oxidation and reduction are taking place in a single step. So we can also call this as a disproportionation reaction. So disproportionation reaction occurs because the same species is being oxidized and reduced in the given reaction. Question 9. The molecular formula C4H9OH represents four different alcohols W, X, Y, and Z. So these alcohols are given. W is a primary alcohol, X is a secondary alcohol, Y is a primary alcohol but branched, and Z is a tertiary alcohol as seen from the structures given. Draw the skeletal formula of Z. So Z is a tertiary alcohol. So what we would have is a carbon atom with an OH group present to which there would be three other CH3 groups attached. So this is the skeletal formula of Z. Acidified potassium dichromate 6 is used as an oxidizing agent in organic chemistry. Give the structural formula of the organic product formed when each of the four alcohols above, and in this case drawn on the left, is heated under reflux with acidified potassium dichromate 6. If you believe that no reaction occurs, write no reaction in the box. So in the first case, we have a primary alcohol. So the primary alcohol will be oxidized to a carboxylic acid. So we will end up with a CH3 group followed by a CH2 group followed by a CH2 group, and then we have CH2OH which will be converted into COOH. So this is the oxidation product of alcohol W undergoing oxidation. Then we have product X, which would be a ketone because X is a secondary alcohol. So this would be CH3 bonded to CH2 bonded to CO, which would be C double bond O, which is bonded to a CH3 group. So this is the ketone formed on oxidation of alcohol X. With alcohol Y, which is a primary alcohol again, we would have oxidation of the CH2OH group into the COOH group. So the product would be CH3 twice, CH and then COOH because the primary alcohol is oxidized to a carboxylic acid. And then we have Z. Z is a tertiary alcohol, and tertiary alcohols do not undergo oxidation. So we would write no reaction. One of the alcohols W, X, Y, or Z drawn here can be dehydrated to give more than one organic product. Identify this alcohol and give the structural formula of the two products. So this cannot be a primary alcohol because when a primary alcohol is dehydrated, it would give only one product because the double bond would be present between the first and the second carbon atom. So this eliminates W and Y as the alcohol that would give two products. Now we have X and Z. So if we look at Z, we've got a CH3 group attached to the COH group. So whether the hydrogen is removed from any one of these CH3 groups, we would end up with the same alkene as well. So what we are left with is X. Now, if X undergoes dehydration with the carbon atom on the extreme right, then we would have the double bond present between the first and the second carbon atom. And if it undergoes dehydration with the carbon atom, second carbon atom from the left, then the double bond would be present between the second and the third carbon atom. So these are two different products. So what we will do here is we'll write alcohol X is our alcohol which would form two products. So product one would be if we have CH3, CH2, then we have CH double bonded to CH2. So this is the double bond between the first and the second carbon atom. And the other product would see a CH3 group attached to a CH group, double bonded to a CH group, attached to a CH3 group. Here, the double bond is present between the second and the third carbon atom. So the name of these products would be but 1 ene as product 1 and but 2 ene as product 2. Question 10. A series of reactions based on propane-1-ol is shown. So propane-1-ol undergoes reaction 1 in which we have introduction of a double bond and elimination of a water molecule. So this is an example of a dehydration reaction. Then this dehydrated product, which is the alkene, reacts with steam and a catalyst to form compound U. So this undergoes hydration, which means compound U is an alcohol. And then alcohol reacts with HBr and undergoes nucleophilic substitution to form compound V. So compound V would be C3H7Br because OH will be replaced by Br. And in reaction 3, the compound V is converted back into the alkene. So this is removal of HBr. So this is an elimination reaction. So this would require reaction with NaOH plus ethanol plus heat under reflux. And this reaction is also known as a dehydrohalogenation reaction. Now, the reaction that is left is the conversion of a primary alcohol into a carboxylic acid, which is oxidation. And oxidation reaction can be carried out using acidified K2Cr2O7 or acidified KMNO4 plus heat under reflux. So these are all the types of reactions and the different reagents and conditions required to carry out all the reactions shown in this organic synthesis flow diagram. So suggest a suitable reagent and condition for reaction 1. So we have dehydration taking place. So a suitable reagent and condition would include either Al2O3 at 350 degrees Celsius, or we can have concentrated H2SO4 used at a temperature range between 170 to 180 degrees Celsius. Write an equation for reaction 2 using square brackets O to represent the oxidizing agent. So we have CH3, CH2, CH2OH undergoing oxidation to produce CH3, CH2, COOH, and the hydrogen that have been removed would form H2O. So in total, we need two atoms of oxygen. So we balance the equation out by writing the molar coefficient of square bracket O as 2. Suggest a suitable reagent and condition for reaction 2. So the reagent and condition for reaction 2 is acidified K2Cr2O7 or acidified KMnO4, and in either of these cases we include heat under reflux. Give the structural formula of U and V. So compound U would be an alcohol. So we would have CH3, CH2, CH3, CH2, OH, and then CH3. This would be a secondary alcohol because we can have formation of a secondary alcohol or a primary alcohol. But the secondary alcohol would be formed in a greater quantity than the primary alcohol. But just to show that another possible product is also there, so it could be CH3, CH2, CH2, and then OH. This is the primary alcohol that can form. And because of this, the product V would depend on which alcohol is formed. So if it is a secondary alcohol, then product V would be CH3, CH2, Br, because OH is replaced by Br, and then CH3. And if it is the primary alcohol, then compound V would be CH3, CH2, CH2, and then Br. This will be a primary halogenoalkane. Suggest a suitable reagent and conditions for reaction 3. So reaction 3 is the conversion of the halogenoalkane into an alkene. So this would require NaOH plus ethanol, and then we would also heat under reflux to convert the halogenoalkane into the alkene. Question 11. There are four alcohols A, B, C, and D, which are structural isomers with the molecular formula C4H10O. Alcohol A does not react with acidified potassium dichromate 6 solution, but B, C, and D do. So alcohol A is a tertiary alcohol. B, C, and D can be primary or secondary. All four alcohols react with hot concentrated sulfuric acid to form products with the molecular formula C4H8. All of them undergo dehydration. A, C, and D each give a single product in this reaction. A, C, and D. So C and D are primary alcohols because then only a single alkene would form. B gives a mixture of two structural isomers, one of which shows stereoisomerism. So B is definitely a secondary alcohol because if the OH group is on the second carbon atom and when dehydration occurs, the OH from the second carbon atom and H from the first carbon atom can be removed, or OH from the second carbon atom and H from the third carbon atom can be removed, forming two different types of alkenes. And if the double bond is between the second and the third carbon atom, then we could have cis trans isomers forming. Give the skeletal formula of each of the four alcohols and complete the diagram with the name of the type of structural isomerism shown by each linked pair of compounds. So A is a tertiary alcohol, B is a secondary alcohol, C is a primary alcohol, and D is also a primary alcohol. So for a tertiary alcohol with four carbon atoms, we would have a carbon atom with an OH group, and then we would have three CH3 groups attached to the three other remaining positions on the alcohol. For a secondary alcohol, we would have a carbon atom with one hydrogen, one OH group and then a CH3 group on one side and a CH2 and a CH3 group on the other side. For primary alcohols, we can either have a straight chained alcohol with CH3 followed by three CH2s and then an OH group, or we can introduce branching in the rest of the molecule, but the OH would be attached to a carbon atom which has two hydrogen on it, making it a primary alcohol. So we are left with a CH group attached to two CH3 groups. So in this way, we have two different primary alcohols, a secondary alcohol and a tertiary alcohol formed. Now we need to put down the structures of these alcohols in the skeletal formula. So for A, we would have this representing the skeletal formula of the alcohol that has already been drawn. For B, it would be four carbon atoms drawn this way with an OH group on the second carbon atom. For C, it would be four carbon atoms drawn this way with the OH group on the terminal carbon atom. And for D, we would have a structure like this with a CH3 group present on the second carbon atom. So these are the skeletal formulae of the four different alcohols that have been provided to us with the formula C4H10O. And now to identify the isomerism present between the alcohols. So between A and B, the isomerism is introduction of branching, and introduction of branching is a type of a chain isomerism. Between B and C, we have shift of the position of the OH group. So this is what is known as a positional isomerism. And between C and D, again we have introduction of branching. So branching is present in chain isomerism. So these are the three different types of isomerism that exist between A and B, B and C, and C and D. Give the names of the two structural isomers produced by the reaction of B with hot concentrated sulfuric acid. So we would have a double bond present between the first and the second carbon atom, forming an alkene called but1-ene. And if the double bond is present between the second and the third carbon atom, the alkene produced would be called but2-ene. State which of these two isomers shows stereoisomerism. Explain why this molecule is capable of showing stereoisomerism. So but2-ene will show cis trans isomerism due to two CH3 and two H groups present on two carbon atoms with a double bond between them, resulting in restricted rotation about the carbon-carbon double bond. So that means that if both the CH3 groups are on the same side of the double bond, then they cannot be rotated to face in the opposite direction to each other. And if they are present in opposite direction to each other, they cannot be rotated to be in the same plane or the same side of the double bond. So this is the reason why cis trans isomers are present in the molecule of but2-ene. Draw the displayed formula to show the two stereoisomers. So if you have to draw displayed formula, so we can have a carbon double bonded to a carbon atom with hydrogen pointing on one end, and then we have CH3 pointing towards the other side of the double bond. So this is an example of a cis isomer. And as for the trans isomer, we would have the carbon-carbon double bond with the CH3 groups present pointing towards the opposite sides of the double bond. And in a similar manner, we would have hydrogen atoms pointing towards the opposite side of the double bond. And this is what is known as a trans isomer. Question 12. A, B, C, D, E, and F are all structural isomers with the molecular formula C4H8O. D, E, and F all decolorize bromine and effervesce slowly with sodium metal. So they have a double bond present and they have an OH group present in them. So they are an alkene and an alcohol group. E shows geometrical isomerism. Only D has a branch chain. So D is branch, E shows cis-trans isomerism or geometrical isomerism. So in E, the double bond will not be present on the terminal carbon atom. None of these isomers contain oxygen atom bonded to a carbon atom involved in pi bonding. So a carbon double bonded to a carbon atom will not have the OH group present on it. None of these isomers contain a chiral center, so they will not have any carbon atoms with four different groups attached to them. Give the structures of D, E, and F. Show the two stereoisomers in E and label the stereoisomerism shown. Okay, so in D, we've got a double bond, an OH group. Branching was present in only D has a branching. So branching is present in D, and we've got C4H8, and the OH cannot be attached to the terminal carbon or the double bonded carbons, and the double bond has to be on the terminal because it will not show cis-trans isomerism. So we start off with CH2 double bonded to a CH group, and it has to have a branch as well. So instead of CH, we can actually include a branching on this carbon by introducing a CH3 group here, and then this can be bonded to a CH2 OH group in order to form a primary alcohol as well. So C1234, H3, 4, 5, 6, 7, 8, and O. So we have met all the requirements given in the question. E will show cis-trans isomerism, so the double bond has to be between two carbon atoms that have two R groups attached to them. So the same groups would be hydrogen on them, showing cis and trans isomerism. So two hydrogen pointing on one side of the double bond will show the cis isomerism, and on the opposite side will form the trans isomer. Now we are left with two carbon atoms and an OH group. So one of these will be a CH3 group and the other has to be a CH2 OH group. And in the trans isomer, CH3 stays on the same side while CH2 OH switches sides to give rise to the trans isomer. So the one on the left is a cis isomer and the one on the right is a trans isomer. And as for compound F, it has to have a double bond between the first and the second carbon atom, CH2 double bonded to CH. It should not have branching and it should have a primary alcohol. So we can introduce CH2 in between CH and the terminal CH2OH group. So here we have a straight chain compound with a double bond between the first and second carbon atom, eliminating formation of cis and trans isomers, and an OH group present on the other terminal of the carbon chain. Identify the gas produced during the reaction of each of these isomers with sodium metal. So sodium will displace hydrogen from the OH group. So the gas produced would be hydrogen gas because sodium displaces hydrogen. So hydrogen, instead of carrying a positive charge, will now become atomic hydrogen. Two atoms of hydrogen combined together will form molecular hydrogen gas. Question 13. Some reactions involving ethanol are shown. So ethanol is formed from reaction 1, in which we have chloroethane converting into ethanol. So this would be a reaction in which the halogen alkane reacts with NaOH only, and the alcohol converting back into the chloroethane would be either reaction with HCl or PCl3 plus heat or PCl5 or SOCl2. And in reaction in which the halogen alkane is converted into compound X, we heat with NaOH in ethanol. So this would result in the formation of ethene because this eliminates hydrogen and chlorine from chloroethane. So CH2 double bonded to CH2. This would be compound X, and compound Y would be distilled with acidified K2Cr27. If you are distilling it, that means you are obtaining the aldehyde. So this would form CH3CHO, ethanol. Give an equation for reaction 2, including the reagents needed for the conversion. Reaction 2 would have CH3, CH2OH reacting with, let's use the first reagent, HCl, resulting in the formation of CH3, CH2Cl, and we would have formation of 1 mole of water. State the reagent and conditions required for this reaction. For reaction 1, reaction 1 would need NaOH and it would need the conditions heat under reflux for the conversion of the chloroethane into ethanol. Identify the organic product Y which is distilled out of the reaction mixture. The organic product Y is ethanol, which is CH3CHO. The aldehyde is distilled off. Explain in terms of the properties of and intermolecular forces in CH3, CH2OH, and Y. Why the chosen condition for the reaction ensures that Y is the product. Okay, so aldehyde CH3CHO will have a lower boiling point than CH3COOH, as CH3COOH will have hydrogen bonding present. Hence, at a lower temperature, it is ascertained that the aldehyde would be distilled out before the carboxylic acid is produced. So, the aldehyde would have dipole-dipole attractions present, which are weaker intermolecular forces than hydrogen bonding. So, aldehyde would have a lower temperature. If we set the distillation temperature to the temperature of the aldehyde, once the milder oxidizing agent, which is acidified potassium dichromate, converts the primary alcohol into the aldehyde. The temperature for distillation would be reached, and the vapor that we would collect as a liquid by condensing it would be the aldehyde before it has been converted into the carboxylic acid. And it will not be the carboxylic acid because the boiling point of the carboxylic acid, due to hydrogen bonding present, would be higher than the boiling point of the aldehyde produced.